Have you ever stopped to think about how your phone, your laptop, your smart TV, and literally millions of other devices can all be using the same wireless network at the exact same time without it all just collapsing into chaos? Well, that's the magic we're going to unpack right here, right now. I mean, really, think about it. It seems like it should be impossible, right? All those signals flying through the air at once. The secret, it turns out, is a brilliant set of rules and techniques that have been evolving for decades. And the master key to all of this is a concept called multiple access. You can think of it as the official rulebook for the airwaves. It's what tells every device how to talk, so it can be heard clearly without shouting over everybody else. So let's dive into how it all works. So here's how we're going to break it down. We'll start with the classic techniques that got this whole party started. Then we'll get to the real game changer, a technology called OFDM. After that, we'll see how it evolved for the modern world, and then we'll tie it all together to see the full journey. Okay, first up, let's go back to the beginning with the foundational methods. These were the original big ideas for solving the sharing problem, and each one did it by, well, slicing up our limited resources in a totally different way. The very first method is FDMA, which stands for Frequency Division Multiple Access. Now, this one is probably the easiest to understand because it works just like your car radio. Every user gets their own private, dedicated frequency. You're on 97.1, I'm on 102.5. Simple. This is the tech that powered the very first generation of cell phones. Yep, 1G. And you know, the best thing about FDMA was its simplicity. It's pretty easy to set up, and you don't need any complicated timing. But it has a huge flaw. It's incredibly wasteful. If you're assigned a channel but you're not talking, that channel just sits there, completely empty. Nobody else can use it. That inflexibility is exactly why we needed something better. So to fix that wastefulness, along came the next evolution, TDMA, or Time Division Multiple Access. With TDMA, everybody shares the exact same frequency channel, but they take turns using it. It slices up time instead of frequency. It's like being in a meeting where you can only talk when it's your turn. This was the tech behind 2G networks, which you might know as GSM. Now, TDMA was a really big improvement in efficiency. By sharing the channel, we could suddenly fit way more people into the same amount of spectrum. The catch? Everything had to be perfectly synchronized down to the millisecond. And because you had to wait for your specific time slot to come around, it could introduce a little bit of lag. Okay, now this next one, this is where things get seriously clever. It's called CDMA, or Code Division Multiple Access. With CDMA, everybody talks at the same time on the same frequency. How is that possible? Well, the magic trick is that every single user is given a unique secret code. Your phone is programmed to listen only for its code and to treat every other signal as just random background noise. This mind-bending approach was the heart and soul of 3G. The payoff for this complexity was massive. CDMA gave us a huge jump in network capacity, and it was naturally really good at handling interference. The downside, though, was that it required some serious engineering. The phone's receiver had to be powerful enough to pick out one specific coded signal from a sea of noise. And it needed strict power control to make sure no single user was shouting and drowning everyone else out. So those first three, those are the classics. But as our appetite for mobile data just exploded, we needed more than just an improvement. We needed a revolution. And that revolution came in the form of a technology called OFDM. So OFDM takes a totally different approach. Imagine you have a huge fire hose of data. Instead of trying to shoot it all through one giant nozzle, OFDM splits it up into thousands of tiny little streams and sends them all in parallel on their own little mini carriers. And the orthogonal part is the secret sauce. It means these carriers are packed incredibly close together, but are mathematically designed so they don't interfere with each other. This is the engine that powers 4G LTE and pretty much all modern Wi-Fi. And the benefits were just incredible. OFDM is super efficient with spectrum, and it's a beast at handling signal reflections, what we call multipath fading, which is a huge problem in cities with lots of buildings. It definitely has its own technical hurdles, but its advantages are what made the fast mobile internet we take for granted today even possible. But here's the thing. OFDM, at its core, was about how a single person could send a ton of data really, really fast. The next obvious step was to figure out how to share that amazing power among lots of people at once. And that brings us to the OFDMA revolution. OFDMA basically takes that giant pool of thousands of mini carriers from OFDM and starts playing air traffic controller. It says, okay, you over there, you get these 20 carriers.
You need to upload a big file, so you get these 200. And you're just sending a text, so you only need these 5. It's incredibly dynamic and flexible, letting the network give out resources precisely where they're needed, millisecond by millisecond. This is the core of 5G and Wi-Fi 6.
The biggest win here is that amazing flexibility. The network can serve tons of different users all at once super efficiently. The only real trade-off is that all that management, figuring out who gets what and when, adds a whole new layer of scheduling complexity. But it's a trade-off that's well worth it. So let's pause here, because this is the big aha moment. If you only remember one thing, let it be this. OFDM is the technique for how a single user's data gets put onto the airwaves. OFDMA is the method for how those airwaves get shared among many different users. OFDM is for one, OFDMA is for the whole group. Okay, let's pull back and look at the whole journey. When you put it all together, you can really see the incredible story of how we got from making a simple phone call to streaming ultra-high-def video from anywhere. This table really says it all, doesn't it? We started with the simplest idea, dividing up the frequency for 1G. Then we got smarter and started dividing up time for 2G. Then came the genius idea of using unique codes for 3G. And finally, for 4G, 5G, and modern Wi-Fi, we're dividing up thousands of tiny subcarriers, first for a single user, and now dynamically for everyone. And here it is laid out as a simple timeline. Each generation of wireless tech was really defined by its new, more efficient, more clever solution to this multiple access problem. It's just a clear, straight line of innovation leading right to the amazing performance we get with 5G today. So let's wrap this up with the key things to take away. The entire history here is really a quest for more and more efficiency. You've got the classic methods of slicing up frequency, time, and code. Then you have the revolutionary modulation technique, OFDM, that really unlocked the speed of 4G. And finally, you have its evolution, OFDMA, which gives us the super flexible access that powers 5G and Wi-Fi 6. And that brings us to one final thought. We've come so far from dividing a few radio channels to juggling thousands of subcarriers in real time. But as we start connecting billions more devices, everything from self-driving cars to augmented reality glasses, what new access method will we need for 6G and beyond? What's going to be the next great challenge in sharing our digital airwaves?